Welcome to Math 31. This is a lesson on curve sketching. So moving away from the extreme applications and concentrating instead on just graphing fairly sophisticated functions. I'm going to summarize the things that we are going to be covering in the next few units and then start with vertical asymptotes. So the general method to sketch functions goes like this. I didn't indicate this on your notes, but you should always find the domain and range. Might go without saying, but it does matter, particularly the domain. And then find the x and y intercepts, just like you would have back in the old days. Set x equal to 0 to find the y-intercept, set y equals 0 to find the x-intercept. Now, symmetries is interesting because we looked at this way back in the pre-calc days, and it comes in handy. It's not essential, actually. Many people forget to get symmetries, and it doesn't make much difference. But it can save you a little bit of time if you do note it, and it can give you more information about the graph, just sort of helping you to see the whole thing. You've got to recognize that you will be graphing these without a calculator. Although you can check with a calculator, the graph has to be formed itself manually. So anything that you can do to make your life easier is a good thing. Find asymptotes. Now, asymptotes, some of you have some background on asymptotes already. I'm going to formalize some of this: vertical, horizontal, and then oblique asymptotes, or slant asymptotes, which you haven't seen much yet. First, derivative analysis. This we've looked at already. And we'll look at it more in a real hardcore graphing context, but we've done it. And then second, derivative analysis, we haven't really done yet, although we have done lots of second derivatives. So if you take a look at the list, you'll see that there really isn't all that much that is really new. The asymptotes basically are familiar: symmetries, x and y intercepts, domain and range, first derivative analysis. But the second derivative analysis does introduce a new concept or two, and of course slant asymptotes. But mostly it's just a matter of putting all this together. So vertical asymptotes, just to get going on this, it'll be familiar too. But if you're to consider this graph, pretty basic rational function, a reciprocal function, 1 over x plus 2. Now, without doing anything fancy with it, you'll note that x cannot be equal to negative 2. So the vertical asymptote in this case is at x equal negative 2. So wherever that denominator was equal to 0, that's where our vertical asymptote is going to be. So it's undefined. The function is undefined at x equal negative 2. So that's not a difficult one. But to make a few observations about it, if we were to take a look at the left and the right-hand limits, you'll notice in this case the left-hand limit right there, as x approaches negative 2 from the left, so here's your negative 2, the function, the limit of the function is, well, negative infinity. There is no limit. It goes down forever. And the right-hand limit, as we approach negative 2 from the right side, it goes up forever. It increases without bound. So this is typical for vertical asymptotes. If we do have a vertical asymptote, it means the function, the limit, will either be plus or minus infinity, or there will be no limit. It will either increase or decrease without bound. So in general, if a function has a vertical asymptote at x equal a, if the limit as you approach that a value from the left is equal to plus or minus infinity, so it either increases or decreases, could be either, or and then for the right-hand limit, the same thing. Must be the case. It has to keep increasing or to keep decreasing. So it makes sense. That's just a different sort of formal way of looking at something that you already know. Now, before we start doing lots of these, we actually won't do lots of them before we do a few of them, don't make a mistake that you often see with this function, x squared minus 4 over x minus 2, or ones like this. This is a rational function, and by inspection x cannot be equal to 2. But that's not an asymptote, or not a vertical asymptote. This would turn into y is equal to x plus 2 multiplied by x minus 2, and you've seen this one enough times that it's not going to be a big deal. But it would then break down to y is equal to x plus 2. So it looks like a linear graph, but you have a point of discontinuity. At x equal 2. So that's not to be confused with the asymptote, because in fact the limit as x approaches 2 from the left, in this case, is equal to 4. And then the limit as x approaches 2 from the right side is also equal to 4. So there is a limit for this function. It is not increasing or decreasing without bound. It's going to be approaching 4. So not a big deal, but you want to make sure you don't make a mistake like that. Then let's launch into a few questions. Nothing really outrageous happening. So f of x is equal to 2 times x squared plus 1 over x squared minus x minus 2. And we want to get the vertical asymptotes for this one. If we were to break this one, the denominator down, f of x is equal to 2 times x squared plus 1. Factor that denominator, and we'd get x minus 2 times x plus 1. And then we set the denominator to 0. So x minus 2 is equal to 0. So x is equal to 2. X plus 1 is equal to 0, so x is equal to negative 1. So those are going to be the two vertical asymptotes, and the graph will support that. So negative 1 is there, and 2 is there. But the issue really is about the behavior of y equal f of x around, or in the vicinity of the asymptotes. And we have a few problems based on this graph. Like, we don't know whether it's going up forever or going down forever. So what we can do is take a look at the limit as x approaches negative 1 from the left. And if you were going to do this one, and if you want to find out, well, where am I? Am I positive? Am I negative? Am I increasing or decreasing? You could sub in x values close to x equal negative 1. So you could go, for example, x equal negative 1.1, x equal negative 1.05, etc. like that. And what's going to happen if you did plug those ones in? You'd see by inspection y increases without bound as x approaches negative 1 from the left. Now that's not a lot of fun, particularly when the equation's got a little bit more going on to it. But it will always work. It's kind of an Armstrong method. And then do the same thing if you were trying to find the right-hand limit as x approaches negative 1 from the right. You'll see here that x equal, if you plugged in x equal negative 0.9, then x is equal to negative 0.99. Getting closer and closer to 1, you'll see that the limit, it goes down forever. So the limit as x approaches negative 1 from the right is going to be written like that, negative infinity, and so on. So it's a bit of a problem. Now, the way we ultimately get around that little problem is by noting things like first derivative, which can tell us whether it's increasing or decreasing. So we do get some information with it. So there are other ways to recognize the behavior of function around the asymptotes. So we do have some choices. So example would be first derivative analysis. It tends not to be a problem, but if you don't go any further than this, then there's often some confusion about what's going on with it. Now let's do one more. And on this one, we can also come up with some conclusions about the behavior of the function just based on the function itself. So not a difficult one particularly, negative 2 over x plus 3 squared. And I think most people are pretty comfortable. Set that denominator to 0. X plus 3 squared is 0. So x plus 3, take the square root of both sides, is equal to 0. So x equal negative 3 should be a vertical asymptote. And in fact it is. But what's interesting about this graph is from both directions, the limit as x approaches negative 3, it goes down forever. And if you did each limit separately, the left-hand limit and the right-hand limit, of course, you'd get these values. And what you can do is, note, with respect to the sign of this thing, it must be negative. This one here is always going to be negative on top, because that's negative 2. The denominator will always be positive. So therefore, it must approach. So y must approach negative infinity, not positive infinity. So once you establish that there's a vertical asymptote at that point, it cannot be rising. It simply cannot cross the x-axis. It must be negative everywhere. So that's the sort of thing that you can do with it. And so there are methods to get the behavior down for it. So that's it for this particular lesson, a fairly short one. The next lesson will be going through horizontal asymptotes, and then we'll just gradually work our way through some of the methods. Thank you for your time.